The antiderivative is the power rule going backwards. So everything that we learn from the power rule is pretty much the same thing as the antiderivative, but backwards. So you have to have a polynomial, a radical, or reciprocal. So that's the only ones that you could do the antiderivative. And just like that's the only ones you could do for the power rule. So the power rule is going forwards. So this one here is forwards. So that one there is finding the slope of the tangent line. And so anytime going forward is finding the slopes. Going backwards is the antiderivative. And that is going backwards. And that's finding the area under the curve or between the x-axis and the curve. So the antiderivative says that if I have f of x here, then I have x to the n. We use a capital F to say that we are going backwards. And what we do, since the power rule is that we multiply the n to the coefficient and then we subtract 1, going backwards says that now I am going to add 1 to the n, and then instead of multiplying, we're going to divide by that on there. So that's the antiderivative. The other thing you need to keep a notice of is since we're going backwards, this one's going forwards. This one here is your d of x, and then you find your v of x, your velocity, the first derivative. Going backwards says that this here is your v of x, and you're going backwards to find your d of x. So that is the difference on there. Okay, so the same rules apply. The variable has to be the base, and there has to be a number as an exponent in order to use the antiderivative, which all of these things do provide. So doing some examples here, if I were to take, notice how this here is your v of x, and now we want to find our d of x. Or this could have been your acceleration, finding your velocity. The main thing is that you're not going forwards, you're going backwards. So here is our polynomial. The base is an x, the exponent is a number. So we could actually figure that out. So now we have 5. And so we are going to add 1 to this. And so we're going to get x plus 5. And then over that is going to be 5. So our answer here is going to be x to the 5th. Now, here is the problem, though. If I were to take the derivative of x to the 5th, the derivative here would be x to the 5th. It would be x to the 5th to the 4th, which is what it says there. But what if I had said x to the 5th plus 7? So if I have that, then when I take the derivative, this is still going to be the same answer, plus 0. So how do I know that if I'm going backwards that I don't have a constant? And the answer is I don't know. So we never know if there's a constant or if it was just 0 to begin with. So anytime that you're going backwards and we don't have enough information, we always say plus c. The constant could be 0, meaning there was no constant, or there could have been a constant such as 7. So anytime you're going backwards, you have to use the plus c, unless they're giving you a specific area. So right now, we're going to use the plus c on all of them. Okay, so looking at this, we're going backwards on this one. Notice that this here is the same thing as before. It's the square root of 3, which is a coefficient of, and the x is not under the radical. So when you're taking the antiderivative of this, you're going to do the exact same thing. So you're going to take this cube root, you're going to add 1, and then divide by it. And so that's going to be that antiderivative. And then this one here is going to be the 1/3. And so what you're going to have, if we could leave it like that. So it's going to be x to the 4th, and then it's going to be, I don't know why we have that minus there. It's going to be 3, which is still there, and then you're going to multiply it by 4. And so we end up getting that. And then what we have here is that this is a constant going backwards. That means that the original one was going to be linear. So it's going to be x, e to the x. This is a coefficient. And then this is x. It's not raised to the x. It's just times x, because this is the same as 2.718x. That's your coefficient there. And then, of course, it's the antiderivative. So we say plus c. So that is your capital F of x. So that's your antiderivative. Okay, so what happens if I have this, which is similar to the power rule? If I have something like this, what we would do is we need to rearrange it. So we would have f of x is going to be x to the negative 1/2 times x to the 4th minus x squared. That's bringing this up to the numerator. And then we are going to distribute that. And so I get x to the, we're adding the exponent, so I have negative 1/2 plus 4. We're not multiplying them. And so this becomes 8/2. And so that becomes 7/2. So that's x to the 7/2 for the first one. And then we are going to do negative 1/2 plus 2. So that's going to be 4/2. So that's 3/2. So that's going to be negative x to the 3/2. So if I have that, I am going to take the antiderivative of it. So I am going to add 1 here and add 1 there. And so what we get is going to be 7/2 plus 2/2, which is 9 halves, and 3/2 plus 1, which is also going to be 2/2, and that is 5/2. So we are going to get x to the 9/2 minus x to the 5/2, and then you have to add it to the denominator. Now here's the thing. Um, I know that I'm supposed to have 9/2 down here, but that is a complex fraction and we don't write that way. So what you do is x to the 9/2. This is a division symbol, so divided by 9/2. So it's x to the 9/2 times 2 9s, because you do the reciprocal to change that there. And so this is over 1, numerator to numerator. It's 2x to the 9/2 over 9. So a better way to write this, and this is also 5/2, right? So a better way to write this is always going to be, if you have that, it's always going to be the reciprocal. So it's 2x to the 9/2 over 9 minus 2x to the 5/2 over 5. And that there is your antiderivative. Could you have written this in a better format? Sure, I would have also accepted the square root of x to the 9th. I mean, this does reduce a little bit more in there, but I'm fine with this. Square root of x to the 5th, and then either one on that. Okay, very good.